Welcome. Welcome to my presentation of translucency sorting. I hope you're all prepared for a somewhat technical talk. I hope it's not too technical, but it's more technical probably than some of the other ones. I'm adapting the presentation I did about this as my thesis defense. I did my thesis on this, and maybe that's something we want to talk about. Here, I wrote it. It's There's a text. You can actually read the whole text, but I wanted to have a presentation that's more Minecraft focused, which makes it probably, hopefully, a little bit more accessible. It's a pretty dry topic otherwise, so I've added more funny Minecraft screenshots. Okay, maybe not funny, but at least they're Minecraft. So it's a kind of academic focused type of presentation, and I used LaTeX. So you know, okay. Well, let's get into it. And this is not that useful. We're going to start with an introduction, wow, and then go through what it's about, and then I'm going to go over the various approaches. And then at number 5, we'll talk about the difficult, like the hard to sort problems that I've solved recently, but the build that does that isn't actually in this mod pack, but the general translucency sorting is in the mod pack. So you can see basically that translucency isn't entirely broken everywhere. Wow. Um, and then in the end, there's like a theory section that I might talk about a little bit. It's kind of intense, and I don't know, maybe we'll do the Q&A and then I can talk about the theory section if someone wants it. Okay, so this is what it looked like before. It was broken. You can see on the left, it doesn't look right. Pieces are missing. How may this happen? Well, um, when we render translucent quads, like the blocks are made of quads. A quad is just a shape in space with 4 corners, and if we render them in the wrong order, then it breaks. And this is not a new problem. Generally, games have translucency, and it's something that everyone needs to deal with if they want to have translucency in their game. And this is not a new problem. I'm not solving a new problem. Like Minecraft has had layer translucency for pretty long, and other games have had it too. But usually, what you find is that either games avoid it entirely, they just don't let you layer more than one layer of translucency, or they use a order independent transparency or translucency approach. One funny thing is translucency and transparency are not the same thing, and the literature actually disagrees on which one is which. So I'm gonna say translucency is when you have stained glass, like you can see the thing behind it. We can go back and you can see like there's something behind it, but it now has a different color. You can still see it, but the color has changed. And transparency is when there's either entirely the thing behind it or none of it. There's just a thing in front of it, like leaves. With leaves, there's like a bunch of holes basically, and that's transparency. And we don't care about transparency because that's just easy. When you render something, it writes the depth of what you've rendered to the depth buffer. The GPU does that, and then it's fine. And then if it renders something in front of it, then it checks, are we closer, are we not closer, by just checking the depth. With translucency, we also do that, but we do need to order it in the right order, so every layer gets blended onto the last. And what Minecraft and Sodium use is ordered rendering, where we just put the quads in a certain order so that when we render them, they end up layering in the right order. you can also, as I said, use order independent approaches where you don't fix the order. They have gotten a lot better, and it's a legitimate approach, but it is not free. So you need to render everything basically 2 times, maybe 3 times, depending on the approach. And that's not great. So, like sodium, for example, is already kind of bottlenecked on vertices on a lot of devices. So if you want to render something twice, it'll probably just take twice as long, which we don't want because taking twice as long is bad. So we don't really want to do that. So I mean, the approaches can work. There's been attempts at order independent transparency, but they have so far not been great. I think there's modern implementations, like some people right now have implemented them and they've been okay. But the thing with just ordering the quads correctly is that it is like nearly free. So that's what I'm doing. The performance is basically free because we have an index buffer anyway, the thing that says in what order we want to render the quads. And we can just change it. We can just make the quads use some other order. And also the other good thing is that we only need to render everything once, which is much nicer than if we need to do gymnastics. There's also like a platform question. You don't really have a good time doing order independent translucency on older devices that don't support new OpenGL features. So that's another aspect. Okay, so how does it work? How do we render things? So this is Hermitcraft, and that's just a translucent layer. You can see it's a lot. I would like it to be less, to be clear. There's like too much of it. A lot of that's a different thing I'm working on, but it doesn't have anything to do with translucency sorting. The caves, first of all, don't need to be rendered, but also we don't really need to render all of the water in the flooded caves. But those are 2 different questions. I mean, the one is just culling, which is just hard on its own, and the other one is if we fiddle with how water is rendered, maybe we can get rid of like water quads that you probably can't see unless you're in spectator mode. But whatever, there's a lot of it. We need to do it pretty fast. And when we have the quads, we do the alpha blending, and we need an order to blend them correctly. And the sections, which is just like 16 blocks cubed, so they're chunks, and then you cut the chunks into vertical pieces. Those are already sorted by sodium, and vanilla also sorts them. So it sorts them by distance. So close things get rendered last, and far away things get rendered first, so that when you render them in order, then you keep putting stuff on top. We only really need to do the sorting within each section, because if you sort the sections and then sort everything inside the sections, then in total it will be sorted. This doesn't apply to anything other than terrain. I have to be clear that we're only doing terrain sorting. We're not doing sorting, at least I'm not doing sorting, between entities, between terrain and entities, between terrain and clouds, or entities and clouds, and all the other stuff. In that case, order independent translucency might be interesting. But we also have fabulous mode, which solves most of the problems with that. This is the formal problem statement. I'm not going to get into it too much, but this is the math problem we're trying to solve. So some of you might know the mathematical term of a set. We have a bunch of quads, which is a set of quads. And then we have vertices, and the quads are made up of vertices. And we assume, this is important, that the quads are flat. So I say the quads vertices lie in the same plane, and a plane in space is just like a flat surface that you can describe by a single point and the direction in which it points. Well, maybe in which the normal points. A point doesn't really point anywhere. The normal is important. I'm going to get back to that. And we use it a lot. And then there's an origin, which is not like you could use a point, but you could also just take a dot product. So you know the direction in which the plane is facing, and then you know how far along that vector it is. And we now want to find the ordering of all of those quads such that it just looks right. Here I describe it as the ones with greater depth are rendered before those with lower depth. And we can also just get rid of it if we can't see the quad anyway, because the quads are always one-sided, so you can only see them if the normal vector is pointing at you. The normal vector always has a 90-degree angle between itself and the surface of the plane. But that's not that important, because usually we can't really take advantage of that optimization, because as soon as you move around, it would be wrong. There's some problems that we can't actually do by just reordering the quads. If they overlap in a cycle, we just lose, because there's no way you can order those without it just being wrong. Because as soon as you render the orange one first, then you have to render the blue one and then the green one, and now you've rendered the green one on top of the orange one, which is wrong. And then you won't be able to see the orange one. You won't be able to see them in the right order. So either the depth is wrong and then you can like see through it, or it's just the wrong layering. And so in those cases, we need to split the quads. Like we could split the orange one in half, and then we have 4 quads, and then there's an order. But we don't know where to split them in this case. But so there, then we need to do the whole quad splitting system, which I will talk about later. And also when it's intersecting, we just immediately need to do splitting, because there's no way to solve it, obviously. Like you can't do anything, any order is just going to be wrong. So I looked at some special cases, and the theory doesn't care about the special cases. It's just, in theory, we just have the same computational complexity anyway. But the special cases are really important in practice. We don't need to do any sorting if all of the quads are aligned to a box and facing outwards. You can see on the left, I have a little graphic of the quads are now thick. Like that's a little bit cheating, but they're thick now. And then on the right, that's what it would look like in Minecraft. I can detect that. You can do math on the normals and how many they are and where they are and like how far along the dot products are and stuff like that. There's another special case, which also happens a lot, which is if they're facing away from each other, you can't ever see the one through the other, because if you remember, we only render quads in one direction. So if you look down in the diagram, you can't see the blue quad because you're looking at it from behind, so it would be invisible. So it doesn't matter what order they're rendered in. If you add the red quad, though, then we would need to render the red quad before either of the green quads. Also, the green quads don't need to be in any particular order because you can't see them through each other. This is a little bit more an extended case. You could have a bunch of quads that have the same orientation, like they're all parallel, but then they face in different directions, either left or right. In this case, it's also pretty simple. We just need to sort them by ascending dot product. So we would say BDE and then CA. But it doesn't really matter. You could also do CA and then BDE. Because, again, we can't see them through each other. We can just see the blue ones through each other and the green ones through each other. And this is what I call static normal relative sorting. And if you actually, this is an interesting demonstration. If you press F3, you can see on the right, Sodium actually tells you how many of what special case it's doing. Because I split it up in static and dynamic sorting. The ones I just showed you were the static ones. There's another static one, which is where we do graph sorting. I'll talk about that in a moment. And then there's dynamic sorting, where we need to change the sort order as you move around the world. With static sorting, we never need to change the sort order. We just do it once when the blocks change, and then it's always correct. And there's, in this world that I'm seeing right now, there's like a lot of sections that don't need any sorting. There's 1,000 sections that don't need any sorting. They have translucency, but they don't need any sorting. Then there's a bunch that are static normal relative, and then there's a bunch of static, and there's also a lot of dynamic, but most of them are actually just not doing any dynamic sorting, so it's quite effective. If we can just get away with only sorting everything once, then that's pretty good, because then it's like literally free. Like we upload an index buffer after building the chunk, and then we're done. And detecting that is not that easy, especially if it's a tricky one. But we have a reasonable amount of time during building to just try a bunch of stuff and then see whether it works. We do all of these special case tests, and then I try and do the graph sort. There's also the special case of distance sorting. In this world, it actually does it a bunch of times, which is pretty rare. That means a bunch of weird stuff is going on, which I guess, given the mod pack, is not that surprising. Distance sorting is only used as a fallback. So that's what vanilla does. It just takes the center position of the quad and reorders the quad such that the one that's furthest away is rendered first. But you can see it's sometimes wrong. So you can make arrangements of quads that just do not sort correctly, even if you sort them by the distance to the center point. This is also why sometimes in vanilla you will have issues. And vanilla also has its other problems. Sometimes it doesn't sort it at the right moment, it doesn't sort it often enough, or it forgets to sort them. There's some issues, and I think we've solved all of them, or at least most of them. The quad splitting branch, I believe, solves all of them. I just wanted to mention that distance sorting is not perfect. The problem is also that distance sorting has weird invalidation. So when you sort something by distance, even if it might be correct, it becomes wrong as soon as you move the camera. There is no way to figure out how far you might need to move the camera or not need to move the camera for it to stay correct. So you might move it half a block and it's immediately wrong again. So then you would need to resort and make a new index buffer and re-upload the index buffer. And we don't want to do that all the time because we actually want it to be correct. And with distance sorting, we don't know whether it's correct. We only know that it's correct until you move. And then it's like, yeah, maybe. So we only really do that in this implementation as a fallback. So when it doesn't work with anything else. Okay, so the other static way of sorting, so where we don't need to update it when you move, is topological sorting. So the idea is, what if we just compare whether we can see the one quad through the other one? Like, are they overlapping visually? And if we just put them in the order where every pair of quads that is overlapping visually has this overlapping relationship satisfied, then we have a correct sorting. And this builds a graph. So a graph is where we have a bunch of nodes, that some object, and then we have a bunch of relationships between those objects, which we call edges. And when we have these relationships of where you can see the one through the other, then it forms a visibility graph. And the positions in which the camera always can you reuse the same sorting, the same order, I call the camera polytope. So if you move a little bit and you're still within the same camera polytope, then the sorting is fine. But if you move too far, then it becomes wrong, because then some other pair of quads is now overlapping that wasn't overlapping visually before. And that's pretty easy to imagine. So if you have two things that are not on top of each other on your screen, but then you move such that they are, then now you're in a different camera polytope. And I just wrote down some math that has to be what has to be true so that you can see two quads to each other. Basically, just if there's a view ray between them, then you can see through them. So we don't need to go through the details. They also have to both be visible. Obviously, if one of them is not visible to you, then then it doesn't need to be sorted. The camera polytope is constrained by the planes of invisible quads. So if you take a quad and you expand it like all the way, because it's flat and it's in space, and if you just expand it, then you have like a plane in space. And if you take all of the planes of the quads that you currently can't see, then you have some space around you where you can move a certain distance. And at some point, then you cross the plane of a quad that you currently can't see, and then it becomes visible. So if a quad becomes visible because you crossed its plane, then you need to rethink the order in which you're sorting things, because now you need to somehow integrate the new quad into your sort order. And previously you could just ignore it because it was invisible. So the triggering, which is the process by which we determine when the sort order needs to be regenerated for a section based on camera movement, uses interval trees and like lists of dot products. It's a little bit involved, and I don't actually go into it in this talk too much. And it's the system that we used to call, or that some people still call, GFNI. Or is it, what is it? Is it GNFI? I don't know. It's a bad name. I don't use the name. Right, that name. I think it was derived from global face normal indexing. Um, DAPA has declared it the canonical name for, I don't know, everything. Um, but what happens is that we figure out the dot products of the planes that cause the triggering, and then there's an interval tree, which is basically just an optimization to figure out in which sections we are going to be crossing these planes. And those sections where we cross one of the invisible quads as planes, we need to redo the sorting. And then Sodium schedules a task where then one of the threads that does chunk building and sorting takes up the task and does the sorting. Yeah, the HackMD is old. Like, don't read the HackMD, read the new text, because the HackMD is somewhat old and a little bit wrong. Not entirely wrong, but slightly wrong, just as an aside. In this nice picture, you might have been wondering, what is this nice picture? This is the space that the camera polytope can see through the quad. So on the left, you have the orange camera polytope. That's like the space within which the camera can move before we need to resort. And then in the middle, between the between the green and the blue, there's the quad. It's just a square or rectangle in space. And then the blue is everything that you can see through the quad from any position in the orange volume. And this delightful diagram I made in Blender, I have a ridiculous amount of geometry nodes that generates the actual shape as a mesh, and then I can export that with SVG. It's kind of funny, not really relevant, but just so you know, this is a vector graphic. I'm very proud of this fact. And as you might be able to tell, Yes, I spent 200 hours on the graphic. Um, as you might be able to tell, the shape is very difficult. It's very complicated. We don't really want to be evaluating this. So the camera polytope it has constant complexity, um, and it takes constant time because we can assume various things about how complicated the geometry is, but it's still not really nice. Like, we don't really want to do that, because you would need to do linear programming and evaluate a billion vertices. Like, checking whether a point is in a polytope is just strenuous. Yeah, linear programming, yay. We don't want to do it like a billion times per chunk. There's also the problem that visibility is not transitive, so you can't just do like quick sort, you know? So we actually need to do topological sorting and not quick sort. With topological sorting, we actually compare all of the edges. Basically, it's just depth first search. And it actually needs the amount of quads squared, which is not great because finding a visible neighbor is hard. So we just need to check all of them. I have had ideas for optimizations like acceleration structures, but building an acceleration structure that tells you which set of like objects, like quads, is in the blue thing is like really hard. And you can construct things where it's like pointy and it'll like poke through things, and it's just generally not nice. I thought about it and was like, no, let's just not do that. So what happens is we instead use the reduced visibility condition, which is where I'm not solving the linear program and I'm just assuming the visibility can come from anywhere. We're not going to limit it to the camera polytope, actually. And this still works. It doesn't always work, but it works in a lot of cases. So now we can do visibility tests, i.e. between two quads, we can check whether they can see each other just with axis-aligned bounding boxes. If they're aligned, if they're not aligned, we need to do some dot product tests and stuff, but we don't have to solve a linear program for every pair of quads. So the structure you can see on the left, we can sort with the reduced visibility condition statically. There's just one sort order where no matter where you look at it, it'll always be correct. And that's what we do during chunk building. We just check whether there is one. And if it is possible, then we just use it. If it isn't, then we need to do dynamic sorting. Sometimes we can also use separators, which is a concept that I'll talk about more in dynamic sorting, where if you have a camera position, the yellow thing, then you can't see something through another thing that's on the other side of a plane that separates the two groups. So we can't see the blue quad through the green quad because there's a plane that separates the camera and the blue quad from the green quad, because light and like the way you see doesn't go around corners. So if we can prove that we can't see two pairs of quads through each other, even though there is a camera position where you could, but not the current one, then we can remove those from the graph. Then we don't need to connect them in the graph, and then finding a sort order might be easier. And I do that sometimes, but it's usually not the case because most of the time I just use graph sorting for detecting whether there's a static sort order. So there's also some problems with graph sorting. So graph sorting statically, if we don't have like a camera polytope on the left, we can't sort that because there's like a cycle and you actually need to constrain where your camera position is to find a sort order. But otherwise, if you are able to look from everywhere at once, which is what we have to do for static sorting, then it doesn't work. And on the right, you see the same scene, but we added a separator in a constrained camera position, and now we can see from the green quad to the blue quad because we would need to look around a corner. Okay, so now on to dynamic sorting. Dynamic sorting is when we generate a new index buffer and a new sort order as you move around the word. Dynamic sorting uses a petition tree, which is also not a new concept. That's something game engines have been using for a long time, but they used to use it instead of a depth buffer. They didn't have a depth buffer, so they actually sorted with a petition tree the whole word. I'm just doing it for translucent objects, but they actually sorted the whole word. And they also split quads into pieces because they really needed to sort everything. Nowadays, it does get used as a optimization and acceleration structure, but not usually for everything. So a valid petition is, in this case, without quad splitting, when there's no quads that go across the cut plane. So we have a plane in space that turns the whole space into two parts, and it's a free cut. And that's what they call it in the literature, and I call it valid because without splitting, it's just we can't do it if we needed to cut through a quad. We can use these valid petitions to sometimes make useful petitions, and a useful petition is when it not only doesn't cut a quad, but it also actually splits the quads into two groups. So there's some quads on the plane that does the splitting, and then there's some on either side. We don't really need to have three groups. We can also just have two, but it needs to at least be two. Otherwise, we're just putting slices in space that do nothing. So with petition trees, we just do the petitioning into useful petitions multiple times recursively. It is not easy if the quads are not aligned, but in most of them are aligned. So most of the quads, if you look at the stage and most of the world, the quads of the blocks are axis aligned. And we can do the splitting in quite a good time. We can just sort the quads, the intervals of the quads along the axis that we're splitting them, and then we can just chop them into pieces as soon as we find a gap. You can see on the right, sometimes it doesn't work. If the quads are weird, then the tree is not a tree anymore, then the tree is a list, which, if you know things about trees and computer science, if your tree is a list, it's not a good tree. Trees don't have nice properties of trees if they have turned into lists. But this doesn't usually happen, so it's fine. We just want things to usually be fine. We can build a petition tree of all of our quads, and then when we generate a sort order, we just take the two petitions and then put all of the indices of the stuff that's on the other side of the petition from the perspective of the camera in the index buffer first. We render that first. Then we render everything on the petition itself, and then we render everything that's in the petition where the camera is. And then if we recurse, then the sort order gets generated correctly. And this only takes linear time because we just need to output the index of everything once. So the construction is kind of slow, but it's much better if it's balanced. And usually it's balanced. Usually we never find petitions that don't work because most of the quads are just aligned to the blocks. And the thing on the right doesn't happen. So the sorting just gets re-triggered when we move across the petition plane. And we have, again, this structure that keeps track of all of the planes. And when we move across them, then we just redo it. And then we get a new sort order extremely quickly. This is an example. I made a bunch of quads. In this case, it's 2D, so the quads are lines. And we always petition multiple at once. So we do all of the petitions that we can at the same time. So in the first step, we're petitioning vertically, and we petition on the blue quad. And then we find a partition that goes between the blues and the greens, but it doesn't have a quad on the plane. And then we also can cut off the orange one. And then within the green groups and the blue groups, we can do it with horizontal cuts. And then we can do it again in the green group. We can do it with diagonal cuts. And these are unaligned partitions. So that's something that the implementation doesn't actually do. And I get into why we don't do that later. Spoiler, it's just really hard. So if we do it repeatedly, then we get cuts everywhere. And then we have a tree that lets us generate a sort order really fast. This is actually I should have shown this earlier. This is how the splitting works. This is how we project the quads onto the axis that we want to split. And then we get intervals. So if the quad is parallel to the axis, then it's interval. If it's orthogonal, then it's just a point. So at points, we can put down a split, but with intervals, we need to make sure that there's a gap between them. And we can do this in n log n time because it's just sorting a list of items. The partition planes are generated greedily. We don't pick a certain axis that might be better. You could do that, but most of the effort would just be wasted, especially in practice. Sometimes it doesn't work. Some instances of the problem just don't work, even if they're aligned. On the left, you have this delightful object, which I also made in Blender. And you can try and partition it, but it won't work because there's always a quad that's in the way. And this is a case where we will need to use quad splitting. And on the right, there's even a simpler case for if you have unaligned quads and just 3 that look like that, you can't partition because there's always one, no matter how you want to cut it, that's in the way. The implementation has a few extensions and special cases that make it faster. So when we descend into the partition tree and we have subset of the quads, then we can apply all of the special cases that I talked about before and apply them again. So we might do static sorting of various types, graph sorting, all of those things. Though that is quite effective, but I don't do graph sorting unless necessary, unless the partitioning fails for some reason. Then sometimes we can save it with graph sorting. We can also do partial tree updates. So if the building of the partition tree takes really long, then it might not take as long if we just have to redo some of it, and then we can patch the indices. And index compression can also sometimes help. The indices, especially in repetitive structures like this one, are often really repetitive, and then we can do like, we can calculate the deltas and then calculate how they repeat and stuff like that. It's pretty primitive, I would say, and it doesn't save that much, but it does work. There's also primary intersector detection. That's something that makes sure that when water intersects with other stuff, like stained glass panes or other structures, then we render it so that there's the minimum amount of like weirdness if we don't do quad splitting. Yeah, that's just a general optimization. So interestingly, partition tree sorting is faster than sorting by distance by around 60%. Because remember, distance sorting sorts by quad distances from the camera. So it's doing actually sorting. So it needs to do n log n work to sort the array of keys by their value. So the keys are how far away you are from the quads, and doing just this general sorting operation on every quad takes longer than reading out the index buffer from the partition tree, because that's a purely linear operation. It just needs to touch everything once. even though it is Java objects. And we know Java objects, if you have a lot of them and you jump around between them, are not that amazing for performance, but it is faster. Um, a lot of them are just arrays of indices, so that helps. Yes, indirection. Um, so the static graph sorting avoids some of the dynamic sorting, so those we just never need to resort. And um, as I was mentioning before, the distribution of sort types varies significantly between the various contents that you could put in a word. And distance sorting is never used in practice. Kind of funny to say that here, when it is being used in this world, there's 22 sections that use it. I would like to know which ones. But it does get used rarely, but 22 is not much. So here's some just statistics. You can see in Hermitcraft, we have a lot of static sorting and a lot of partition tree sorting. Partition tree is like what I just described, the dynamic sorting. In Hermitcraft 7, we have much less statically sorted, but much more that doesn't need sorting at all. And you can see it varies. Oceans have just generally less stuff that needs sorting, but a lot of it can be sorted statically. Performance, these are nanoseconds per quad. Distance sorting generally takes on my computer about like 25 nanoseconds per quad. Tree sorting, like reading out the sort order from the tree, takes around 15. In the ocean, interestingly, it's longer. I don't really know why. I guess it's just the structure of the tree. But building takes pretty long. Building is like 130 or something. And static sorting is even more because it's actually a quadratic process. It's not actually quadratic most of the time on real worlds. Like often you don't build a structure that specifically makes it take quadratic time. Often it fails early and then it goes on and does something else. But this is like not really a thing you could measure easily because it's a quadratic number, but it's still here. So let's get to quad splitting, what I've been working on, what is not included in the sodium build on this server. But so I have extra pictures. We can actually split quads more easily than I thought. For a while, I thought it would be too hard, but then I tried, and then it was like, okay, this is annoying and hard, but it didn't turn out to be as hard as I thought. I thought it would be even worse. The concept is pretty simple. If we're trying to split the quads, instead of giving up when we can't, we just say, okay, just take the quad and turn it into two parts. Usually it's going to be one quad on the one side and one on the other, but sometimes it's also a triangle. So then we need to make a quad that's like broken, a degenerate quad. If the quad is bent, then this process just entirely explodes, and I refuse to deal with that. It's finicky. And there's a lot of research on how to pick the right splitting plane. I don't do that because it is very expensive and usually not necessary. My goal is really to solve like stuff like water and stained glass planes, or some of the mods that have like template blocks that you can make stained glass. So, and those don't hit the really weird cases usually. Um, And this results in a partition tree where there's parts of it, parts of the quad on both sides, that we generated by splitting. And we do also need to do some gymnastics to amend the mesh by the new quads that we added through splitting. But that works. The geometry could be amplified by doing that. It could be up to n squared, which is bad, especially if vertices are bad. But it doesn't happen. It basically never happens unless you really stress test it. And we can also limit how much geometry we generate so that it doesn't, even if such a case does arise, like make your frame rate die or it explode or something. This is a case that I generated artificially to see how far I could go. These are just randomly generated quads with some constraints. And you can see on the right, every quad that was generated by splitting has a different color, and there's a lot of them. Because we just pick one of the quads and then we split everything by the plane of that quad. And every time we do that, we basically double the amount of fragments we have on either side. And this was really useful because it generated really weird data. And now we're at a point where it does not break anymore, at least not with this test. Most of the problems actually were introduced by me uh, generating data that couldn't possibly be valid input. And you can see it breaks down if we like give it enough quads. I don't know if you can see it, but there's like holes, and it's like little bites have been taken out of the quads, and this happens because the errors accumulate, and they every time we do the splitting, we have to reinterpolate all of the vertex attributes. So the UV coordinates which say where the texture is, and the position, and all of the other stuff. Um, and they just get more wrong every time you do the splitting. And if you do it, if there's like n squared geometry at the end, that means for every quad, some of them you did it n times to. And that means there's a lot of floating point error. But there's approaches to avoid that. And I did some literature research on how to do that, but it is very sophisticated and I don't need to. So we're not doing that. It works good enough. Just I wanted to say that you could do it. Yeah, I could also use doubles, but it would probably just let me do it for like 100 more quads before it breaks down again. Um, yeah, the correct approach would be to do all of the splitting math and then in the end calculate the correct positions for everything. And there's approaches to doing that, just it's impractical to implement. Okay, so here's a demonstration of quad splitting working with framed blocks. I don't know whether that mod is in this mod pack, but I think we have a similar one. Right, we have templates too, which I think does basically the same thing. This is just the one that I used for debugging primarily. And it's been very helpful because this is like an actual practical use case. And you can see it can deal with crooked sign, weirdly shaped glass things, a bunch of water. It can deal with fences. It can deal with basically anything. I haven't found issues like with the fuzzing cases with the mod. So we're getting towards the end. I wanted to mention, we do want to eventually, at least that's my plan, eventually release the quad splitting to sodium. I don't know whether it's coming in sodium 0.7 or sometime later, but I do plan on getting it in. And then we have fixed, perfect, amazing, correct translucency, at least for terrain. Don't really need to worry about it. So we will see. Now for underline partitioning, this is math. I did some research on how underline partitioning could work and how complex it is. And I put it in here because it was part of the presentation that this is based on. But I don't think I need to go through it in detail. I think I'm going to go over it briefly, and then if you have questions or specific interest, then we can talk about it. So here's an overview. Okay, the time limit isn't too strict. Thank you. So there's just bad stuff in general, but then the nice stuff is in blue. We have the non-intersecting stuff that we can at least somehow deal with, maybe. Then there's the stuff of that is sortable, because I showed you examples that are not sortable. And some of it is also aligned. And then we have unaligned partitionable, where we need unaligned partitions, like partitions that are crooked in order to actually find a partition that only uses 3 cuts that don't split quads. And then we have aligned partitionable, SNR sortable, and stuff that is always sorted on its own, where we don't need to do anything. The unaligned partitioning problem is, how do we find the partition that goes and splits a bunch of quads into groups, like where the quad is not split? Like no quad should be, like it's a free cut, as I said, and if we know the orientation of the partition, it's fast. So if we already know it's going to be exactly this angle, then we can just project and just do the dot product thing. And it's like a line partitioning, just crooked. But if we don't know, if we need to actually find out the orientation of the partition, then it gets very hard, because there's a lot of different partitions that you could apply. And searching through those is expensive. But this is just a theoretical problem, because no hard cases of that actually appear. And the really hard cases are those where you can't actually find any partition, be it aligned or unaligned. So then we just need to do splitting instead. And splitting can also basically just eliminate the need for unaligned partitioning, because it's much easier to implement. So this is where the math starts. We can parameterize the set of partitions as points in a parameter space, which is more or less the same as normal space. And then we can find a linear mapping between the two. And we can also model the shape of all of the partitions that are useful as an object. So you can see here on the right, I have overlaid the volume of the partitions that usefully that validly partition this quad, which is all of the ones that just don't intersect with it. And when we combine all of the valid partition sets in parameter space, then we can find the useful partition set. And here in red, you can see the useful partition set. And it has 2 blobs, which kind of makes sense, because you can imagine there's a partition you can put between the blue and the green quad. And then there's also one you can put between the green and the yellow quad. So that's why there's 2 blobs and they touch in the middle, because those are the partitions that get really close to the green quad. There's a combinatorial solution where we just pick like triples of vertices to form a plane, because the partitions that are just free floating are not more useful than the ones that are like actually touching quads. And the combinatorial solution is n to the power of 4, which is not good. And we can also formulate it again as a linear programming problem. Yay! I call it linear constraint set because we don't actually have an optimization function. But it has even worse time complexity, because it's like multiple linear constraint sets, because we don't actually have a structure that easily lends itself to linear programming, like doing it all with one linear program, at least as far as I'm aware. And so the problem can be solved with like the satisfiability of a linear constraint set, but it's like even more expensive than just doing it combinatorially. So that was the upper bound on the complexity of unaligned partitioning. The lower bound we can also find by somewhat, and this I didn't really flesh out, but we can transfer the lower bound on linear constraint solving to unaligned partitioning. We can map half-space constraints of a linear constraint set to vertices, and then you can see it kind of looks the same. And if you zoom in really far on, I'm going to go back to this thing. If you like zoom in really far on like the red part, and then it's like flat, and you could use that to kind of model a completely different problem, which would allow us to transfer the lower complexity bound. Okay, I think that's enough math. Conclusion. Usually we need to do OIT. That's what most games do. In Minecraft specifically, we don't. And we can do it very efficiently by doing index rendering and taking advantage of a bunch of special cases and using partition trees. And quad splitting then solves all of the remaining cases, which are pretty rare. And unaligned partitioning, by the way, don't do it. It's hard. Okay, so I have a bunch of Outlook questions. Can we use an acceleration structure? Maybe. It's really hard. Can we do like the static graph sorting within the partition tree? Maybe. Can we do convex partitioning, like where we put together quads and then do graph sorting on them? That might be spicy. And also, how can we mitigate the numerical instability, like the error accumulation? And I looked into that, and it's like annoying, but I put it here because it might be interesting. Okay, so acknowledgements. I would like to thank my advisor, my thesis advisor, my family and friends, Jelly Squid and other contributors to Sodium, other members of the Caffeine Discord server who helped me test, Mutzig Bike for helping me test the quad splitting, and also the author of the frame blocks mod, and everyone for listening. Thank you all for listening. I'm taking questions regarding the presentation.
I have a question about the static sorting. Is there a reason why you can't statically sort the vertices slash quads and then use just a shared index buffer instead of having per, I guess, section statically sorted index buffer? Because that way you also reduce your VRAM usage as well as increase cache.
What do you mean by sharing an index buffer? Like the sort order is going to be different every time we do the static sorting because like the geometry is different, right?
Yes. But instead of, so you sort the quads, so instead of them being sorted.
You mean
index
sorting
buffer.
I know what you mean. We could reorder the geometry for the static sorting instead of using an index buffer.
Yeah.
That is a good point. We could do that. I have not done that. The index buffer approach fits in with the rest of the system more easily. But I guess it is definitely something that could be investigated as a VRAM usage optimization, I guess. Okay. Or maybe even rendering performance. I doubt it actually makes a difference. But probably generally just VRAM usage.
Yeah, the VRAM usage would be very minimal, but it could just help. Just a thought.
It could help a tiny bit, yeah. I think, like I already implemented for the stuff that doesn't need sorting at all, it does share the index buffer, but it doesn't share it if there is a non-trivial one, like one that doesn't just go 1, 2, 3, 4, 5, 6, 7, blah, blah. A question has appeared. The question is, I take it that you're focusing on sorting quads rather than triangles, so you have fewer shapes to work with, right? Yeah, so almost always the quads are fine. So yes, then we just have fewer shapes. The pipeline has started, especially with the quad splitting system to become somewhat hybrid, but it is still basically just quads that are degenerate if we need to represent a triangle. I could maybe, like, if we really wanted to fix issues where bent quads, like such as what water does, if those cause issues and we need to split them or we need to sort them, then it might be a good idea to split them into two triangles and then do something with both of the triangles separately. But it's also just uh, an optimization because sodium renders triangles, but it doesn't render, like, the index buffer is aligned to quads, so we always have 6 indices. So it would be kind of annoying to not always render two triangles together. So I think we're probably not going to use triangles unless it really becomes necessary. I hope that answers it. The question is, I'm an absolute novice when it comes to rendering and optimization. When it comes to learning about this kind of stuff, where's a good place to get started? That's an interesting question, very broad. So what I did is not really like the computer graphics aspect of touching OpenGL and doing stuff with it. I didn't really do a lot of that. I did it a little bit, but I didn't do a lot of that. During the whole experience, I have learned a lot about how sodium works and how a bunch of graphics programming things work and how the pipeline works. But there's still a lot of stuff where I'm like, the other people will know this. Because I specifically focused on the algorithmic aspect of the sorting. Um, so it was, to be clear, it was my master's thesis. So I was doing my, I was looking for a topic, and then I had just stumbled upon this problem and was like, oh, this is interesting. We could do this and that. And I talked to a bunch of people about it on Discord, and we ended up discovering like a kind of working maybe solution, and then it like developed from there. And I think that's like a lot how the various rendering and like optimization problems can develop if you do it with other people. I think in general, just learning about graphics programming, there's shader labs for like specifically shader development. There's a bunch of really good university level lectures on YouTube. Like, I think MIT has one, but there's also other universities that have lectures on graphics programming. I'm sure there's books, but I don't know of them. Like, I haven't specifically read any books about this. Yeah, TU Wien is really good with the graphics programming. They're the graphics programming university. And optimization in general, I guess, I don't know. I don't really just want to recommend, oh, go read the algorithms book, but I think a good foundation in what complexity theory tells you and stuff is a good idea. Yes, MIT also has good courses on it in general. Okay, the next question is, there were a lot of math concepts, half of which I didn't understand in parentheses, which you ended up using. How did you figure out which ones to use? How did you research about those concepts? Were there many concepts you looked into which you never ended up using? So I think a lot of the math concepts I used were either from the research papers that I read on the topic in general, just how petitioning works. There's a lot of research you can find on petitioning. You can find a lot of research on translucency. and order-independent translucency, although that is not as relevant to the work. But I think a lot of the general linear algebra and the algorithms is just from college. I've been through the various linear algebra and algorithms courses that teach those things. And I mean, I'm sure there's obviously there's a lot of concepts in those that I didn't use here, but it ended up being pretty broad, and it was fun to find oh, look, there's a graph thing here and there's a tree thing there, and we can do geometry here and there. And I like geometry problems, so that's why I picked this thing. This question says, will fabulous mode be removed if you fixed all of the translucency sorting issues? As I said earlier, I have not fixed all of the translucency issues in Minecraft. I fixed, with quad splitting, the translucency issues in terrain. And if there are any, I would like to find out what they are so I can also fix them, because they are now bugs. Between entities, between terrain and entities and other stuff, as I said in the beginning, is not really in scope. And fabulous mode is still relevant for that. It might also be an option to have order independent translucency system integrated with this. Because then we might be able to have both very efficient terrain rendering combined with the more flexible OIT approach for stuff that moves around. Because you can't really do this type of system for entities and things that move around continuously, because as you saw, there's a bunch of structures that are built so that we can sort really fast and don't need to resort all of the time. Okay. Are there any other questions? If you don't ask a question, I'm going to throw a fish at you. If you don't ask a question, you're going to get a bad grade. That's how it works. Oh, there's another question. I wrote my thesis on it. Does it mean I have a PhD now? Should we call you Dr. Duria? No. This is a master's thesis, not a PhD thesis. I don't know, you might call it different where you are from, but I am now. New development. I'm starting my PhD in 2 weeks, but it's unrelated to this. And this was for my I guess in other places it's a big project at the end, but we in Germany we do a thesis at the end, and this was the thesis for my master's. So no, you can't call me doctor. That's wrong. You have to wait 4 to 7 years until I'm done with that. Hopefully. Someone wants to ask a question with a microphone, I think. Yes?
Okay, so are there room for improvements within the translucency sorting engine? If somebody made a better sorting engine that wasn't compatible with Sodium's license, what would you do? Would you contact them and try and get them to get the exception, or?
I'm going to answer this narrowly. There are definitely improvements we could make to the engine. I presented a bunch of open questions and further work. So we're open to contributions. Please contribute if you have time, ideas. We're always looking. Also, if you don't want to work on translucency sorting, we're open to contributions on Sodium. Thanks. I think we're done. Thanks for coming, everyone.